Welcome back to Machine Learning for Mathematicians. This is Lecture 4, Automatic Differentiation and How to Check It. Today's reading is Dijksenroth, Feisel, and Ong, Section 5.6, together with Prince Chapter 7 on gradients and initialization, and Bishop Chapter 8 on backpropagation. For Lecture 5, read Sections 5.3 through 5.5, Matrix Calculus, and the Layout Convention. Today closes the first part of this course. Let us start by clearing away two things automatic differentiation is not. It is not symbolic differentiation. No expression for the derivative is ever built, and there is no formula at the end. It is also not a difference quotient. No limit is taken and no step size is chosen, so there is no truncation error to trade against rounding error. Here is what it is instead. Stated so, each half can be tested. First, it is exact. The only error is the rounding of operations the program was going to perform anyway. Agreement with a reference sits at the level of the unit roundoff. Second, it is cheap. The gradient of a scalar-valued function costs a small constant times one evaluation of that function, and that constant does not grow with the number of inputs. Both clauses are claims about arithmetic, so we measure both before the lecture ends. Why should a mathematician care about the answer here? The chain rule as a composition of linear maps is already yours. This lecture adds nothing to it. What is new is that such a composition can be evaluated in more than one order. The orders cost very differently, and choosing the order is the whole of backpropagation. Three procedures answer the same question, and they are not variants of one another. Symbolic differentiation returns an expression, and that expression swells geometrically with depth. Numerical differentiation returns a number, and it trades truncation error against rounding error, so it has a floor. Algorithmic differentiation returns a number 2. Its only error is rounding, and it takes one pass, however many inputs there are. So here's the idea to keep. Only the third of them scales, and not by a trick. It is the associativity of composition, read from the end, nobody reads it from in a calculus course. First, the three quite different procedures that share the name differentiation, and what each of them actually costs. So let us watch symbolic differentiation fail. Take the function sine of u times e to the u over 2, that is 2 operation. Compose it with itself, differentiate the composition symbolically, and count nodes in the expression tree. After one composition, the function has 4 nodes and its derivative has 10. After 6 compositions, the function has 252 nodes, and its derivative has 2,771. The growth factor is the thing to watch. Each further composition multiplies the size of the derivative again by a factor settling towards about 2.45. The product rule duplicates both of its arguments. The chain rule duplicates the inner expression, and no simplification undoes the duplication. So after 6 compositions, the derivative is 11 times the size of the function it came from. Now remember what a network is. A network is a composition of hundreds of layers, not 6. Now the second procedure and why it has a floor. Central differences is the honest version of the difference quotient. Take f at x plus h, subtract f at x minus h, and divide by 2h. Expand both by Taylor. The odd terms cancel, leaving the true derivative plus a term of order h squared. That is the truncation term. Now the arithmetic. Each evaluation of f carries a relative error of at most the unit roundoff, which we call epsilon. Dividing by 2h inflates that error, so the rounding term grows like epsilon over h. The total is therefore one constant times h squared, plus another times epsilon over h. Differentiate that sum and set it to 0. The optimal step scales like epsilon to the 1/3, and the error at that step scales like epsilon to the 2/3. In double precision, that is 9 or 10 digits, and no choice of h does better. Lecture 10 returns to arithmetic of this kind, so keep this. The floor is arithmetic, not a defect. No amount of care removes it, only not taking a difference quotient at all. The third procedure is the one the field actually uses. Algorithmic differentiation differentiates the program that was actually run. It applies the derivative rule of each elementary operation as it is performed. The answer is exact to machine precision, and the work is proportional to the work already done. That bargain is bought with two things. The first is memory for the tape. Every intermediate a backward rule needs must stay alive until the backward pass reaches it, so peak memory grows with depth. That is why training a network exhausts memory when evaluating it does not. The second is correctness only for the branch that was taken. A recorded graph is one path through the program. At a kink, such as a rectified linear unit at 0, the library returns a value fixed by convention. So, the thing to remember, automatic differentiation differentiates the trace, not the source. Where the two disagree, and they do disagree, the trace wins. Next, the object that automatic differentiation actually works on. A program, seen as a graph of elementary operations. Write a small expression the way a machine performs it. Let y be tanh of the quantity ab plus c, all multiplied by the quantity a plus c. A machine does that in 5 steps. First, v1 is a times b. Then v2 is v1 plus c. Then v3 is tanh of v2. Separately, v4 is a plus c. Finally, y is v3 times v4. Each operation is a node, each argument an edge into it. The result is a directed acyclic graph. Notice that A appears twice, in v1 and in v4, and so does C. So A and C each have 2 consumers, and that fan out is the only structural feature that will need thought. The graph is also recorded as the program runs, so loops are unrolled and branches resolved before anything is differentiated. By the time we differentiate, there is no control flow left, only a list of nodes. Forward mode is the first way to evaluate that composition. Attach to every node a second number called its tangent, and push value and tangent through the graph together in one sweep. The rules are the derivative rules, read as statements about pairs. For a product, the tangent of u times v is the tangent of u times v plus u times the tangent of v. For a composition, the tangent of g of u is g prime of u times the tangent of u. Now seed the input tangent with a vector v. The sweep returns jv. Seed instead with a jth standard basis vector, and we get one column of the Jacobian. So the whole Jacobian takes one sweep per input. Forward mode also needs no tape since the tangent arrives with the value. Here is what to keep. Forward mode is cheap in outputs and expensive in inputs. A loss function is exactly the wrong case for it. Reverse mode goes the other way. Run the graph forwards and store it, then sweep backwards, carrying each node's adjoint, written v-bar, the sensitivity of the output to that node. Seed the output adjoint with a vector w, and the sweep returns j transpose w, one row of the Jacobian, when w is a basis vector. At a node, the adjoint of v sums over every consumer u, the transpose of the partial of u with respect to v applied to the adjoint of u. That sum is where the mental model breaks. Take the graph from a couple of frames back, where I fed both v1 and v4. The adjoint of A is b times the adjoint of v1 plus the adjoint of v4. The node is not finished until both consumers have reported. So nodes are visited in reverse topological order, not in reverse order of creation. One reverse sweep gives the gradient of one scalar with respect to everything. A network has one loss in millions of parameters. So let us measure the cost difference. Take a function from n dimensions to a single number built out of tanh, sine, and a sum of squares. Its Jacobian has a single row. Now time forward mode against reverse mode in double precision. Read the table honestly. At the 3 smallest sizes, the timings say almost nothing about either algorithm. They are dominated by the fixed overhead of the transform machinery, which is why the ratio wanders downwards rather than upwards. The pattern shows up only at the largest size. Reverse mode does not move, while forward mode grows by a factor of about 30 by the time there are 1,000 inputs. And throughout, the 2 modes agree to about 1 in 10 to the 16th, which is machine rounding error. Those timings come from 2 threads of an Intel Xeon, running PyTorch on CPU only. Now the heart of the lecture. Reverse mode is the adjoint of a linear map, and it is nothing more than that. Let us state it in the form you already know. For a map f from n dimensions to m dimensions, differentiable at x, the derivative at x is a linear map. It is the map that makes f of x plus k equal f of x, plus that map applied to k up to higher order. The derivative of g composed with f is then the derivative of g at f of x composed with the derivative of f at x. For a network, a composition of layers fl down to f1, the derivative is the product jl through j1. Notice that nothing here has formed a matrix. That product is a composition of linear maps, and matrix multiplication is only one representation. Composition is associative, so the product brackets from either end. So the idea to keep the chain rule says the composition holds. Backpropagation says which way to bracket it, and that is the only content of the distinction. Here is the definition you already own. Let J be a linear map from V to W between inner product spaces. The adjoint of J is the unique linear map from W back to V with the following property. The inner product of JV with W equals the inner product of V with J star W for every V and every W. In coordinates with the standard inner products, that adjoint is exactly the transpose. The one property we need is that adjoint's reverse composition. The adjoint of AB is the adjoint of B times the adjoint of A. Now apply that to the layer product. The adjoint of JL through J1 is the adjoint of J1, then J2, and so on up to JL. So each layer is asked exactly one question. Given the adjoint of your output, what is the adjoint of your input? Lecture 6 does this layer by layer. So here is the sentence to keep. Reverse mode automatic differentiation is the adjoint of the derivative, applied one layer at a time in reverse order. That sentence is the entire algorithm. So what does the backward sweep actually need? It needs only the map that sends W to J transpose W. That is called the Vector-Jacobian product, and it never asks for J itself. One reverse sweep computes it at a small constant times the cost of the forward pass. Obtaining all of J costs one reverse sweep per row, or one forward sweep per column. For loss, there is a single output, so the whole gradient is one sweep. Now the memory arithmetic, for one affine layer taking n inputs to m outputs. Written as a matrix, the derivative of the output with respect to the weight matrix holds m squared n entries, a factor of m more than the weight matrix itself. The backward pass stores none of them, only the outer product of the output adjoint with the input. With m in the thousands, that factor decides whether the object exists. Lecture 6 is this argument in full. Now let us check the adjoint identity numerically. Take a map from 3 dimensions to 3 dimensions built from a tanh, a square, a sine, and a sum of squares at a random point. Forward mode gives us JV. Reverse mode gives us J transpose W. Those come from entirely different sweeps over the graph, so the identity tests both at once. In code, it is 4 lines. Call JVP for the forward direction, call VJP for the reverse direction, then form both inner products. Now run 5 random trials with 5 random vectors W. The worst disagreement between the inner product of JV with W and the inner product of V with J transpose W is about 2 in 10 to the 16th. That is machine rounding error, 1 unit in the last place. So the identity is not approximately true here, it is exactly true. What the number measures is the arithmetic of the check itself. Finally, the part of today that outlives this lecture. Gradient checking, stated once as a discipline rather than a habit. Now we measure the floor we derived earlier. Take sine of x squared plus e to the x over 3 at x equal to 1.3 in double precision against the derivative in closed form. Sweep the step size from a tenth down to 10 to the minus 14 and record the relative error. The shape is a U, and the U is the whole content. Coming down, the error falls by 2 decades for every decade of step size, exactly as the truncation term predicts. It bottoms out at about 1 part in a billion, near a step of 10 to the minus 5. Then it climbs again, like 1 over h, until at the smallest step, only a single digit is correct. And that bottom sits within a decade of the step theory predicted, epsilon to the 1/3. So a central difference will never do better than roughly 9 digits. Automatic differentiation has no such floor at all. The whole engine is about 20 lines. A value stores four things: its data, its gradient, the parents it was built from, and a closure holding one local rule. Take multiplication. It builds an output value whose data is the product and whose parents are the two inputs. Then it installs a closure. That closure adds to the gradient of each input the other input's data times the gradient of the output. That is the product rule in two lines. Notice that it accumulates rather than assigns. That is the fan-out sum from earlier, and it is why a node with two consumers comes out right. The backward sweep then does two things. It builds a topological order by walking the parents recursively, marking every node it has already seen. Then it seeds the output gradient with 1 and calls each closure once, in reverse order. No tape format, no graph library, no framework. A value, a closure, a sort, and a loop. Now three independent routes to the same gradient. The first is by hand on a two-layer map. Z2 is W2 times tanh of W1x plus B1 plus B2 scored by squared error. Each line of the backward pass is the transpose of the forward line it came from. The adjoint of Z2 is Z2 minus Y. The adjoint of W2 is the outer product of that with the hidden activation. The adjoint of Z1 multiplies by 1 minus tanh squared, and the adjoint of W1 is another outer product. The second root is autograd. Across all four gradients, dW1, dB1, dW2, and dB2, the worst disagreement is about 2 in 10 to the 16th, which is machine rounding error. The third root is the 20-line engine from a moment ago, which agrees with torch on all three partial derivatives. 3 implementations, 1 number. Now let us break it on purpose. The backward rule for tanh is 1 minus tanh squared. Write 1 plus tanh squared instead, and change nothing else. The relative error in dW1 is then about 2.3, which is to say completely wrong. And here is the uncomfortable part. The forward pass is untouched, nothing raises an exception. The loss still falls, the network still trains, just worse. No training curve will tell you. Then the finite difference probe, which needs no autograd at all. For the first entry, finite differences and autograd agree to 8 decimal places at about minus 3.95. The buggy version says minus 4.98. That is enough to reject the bug, and it is what a custom kernel leaves you. So the sentence to hold on to, a wrong gradient does not crash, it ships. The only thing that finds it is a comparison you decided to make before you needed it. So here's the discipline, stated once and used for the next 28 lectures. 6 steps. 1. Derive it on paper with a layout convention written down beside it. 2. Implement it separately from the derivation so that the two are capable of disagreeing. 3. Compare against autograd on random input in double precision. Random because structured input can satisfy a wrong formula by accident. Double because in single precision you cannot tell a bug from rounding. 4. Where there is no autograd to compare to, use central differences at a step near epsilon to the 1/3, expecting 9 digits and no more. 5. Choose a tolerance you can justify from the unit roundoff and the number of accumulated operations and not from the number that made the test pass. 6. Build a control that must fail. Flip one sign, run the check, and confirm that it rejects. Lecture 11 and Lecture 12 are the first 2 places we use all 6. That 6th step is the one people skip. It is the one that catches a check, which was never testing anything. A check that has never failed is not evidence. Let me gather the 5 things worth keeping. First, 3 procedures share the name differentiation. Symbolic builds an expression that swells geometrically with depth. Numerical trades truncation against rounding and has a floor. Algorithmic differentiates the program that ran. Second, a program is a graph recorded at runtime, so control flow is resolved before anything is differentiated. Forward mode returns a column of the Jacobian, reverse mode a row. Third, reverse mode is the adjoint. The inner product of JV with W equals the inner product of V with J transpose W, check to machine rounding error. Adjoints reverse composition, so backpropagation is the layer adjoints applied in reverse order and nothing else. Fourth, the cost. Both modes agree to machine rounding error, and reverse mode does not slow down as inputs are added, while forward mode grows by a factor of about 30. Fifth, derive it, implement it, compare it, then break it on purpose. One wrong sign in the tanh backward puts a relative error of about 2.3 into a weight gradient. That closes part 1, the dictionary. You can now read an equation and find the line of code that computes it. Next time we do matrix calculus properly. Numerator against denominator layout. The Jacobian of an affine map. The trace identities worth memorizing, and where all those transposes come from.